In this video, I want to explain how a rainbow works. They're such a lovely phenomenon, and I got curious about how they happen. It ends up working not exactly like I thought going in. My plan is to keep it simple, no math, just a qualitative look at what happens to the main rainbow. Let's start with a few basics. I suspect all of you know this already, but just to make sure we're on the same page. The first thing is white light is just the sum of all the colors. They're all there, all the colors in the rainbow, as they say. The second is that light is bent as it goes from air to water or glass. The image is a laser pointer beam as it goes into the water surface. You can see a distinct kink as the beam enters the water surface. We can see the beam because there's steam over the water and the water is kind of dirty. Last, the bending depends on what color the light is. This is a picture of the sunlight coming through the beveled glass of my front window. It's bent, and the colors separate out since they're bent by different amounts. Now let's just think about what we can figure out just from looking at the rainbows. We know they need sun and rain. The sun has to be kind of low, shining in your back, and there has to be rain over the whole length of the bow. I'm sure we've all seen this sort of partial rainbow, which is usually caused by rain in one place and not in another. Another odd thing is that the sky looks lighter inside the bow than outside. This is hard to see if the rainbow isn't nice and bright. And the dark region, interestingly enough, is called Alexander's dark band. To look what's going on, we're going to use an approach called ray tracing that was developed to design things like camera lenses and consists of dividing the light coming into the lens into small bundles, rays, and then following each ray as it goes through the lens. Here's a sketch of a lens with light, let's say sunlight, coming in from the right. We look at a sequence of rays moving from the center of the lens to the edge, and then you follow where each one goes. Because the lens is symmetrical around that central ray, we can just look at one plane. Every other plane will have the same shape. What we see is that all the rays converge at one point, which is what we expect. The last piece we need before we start is the shape of the raindrop. Turns out they don't have the tail like they show in the cartoons, they're just round. Here's a picture of a drop falling. I don't know that we really needed that picture, but it was fun getting it. It looks red because I had to use food coloring. It's hard to see the edges if it's clear. So let's apply ray tracing to the spherical raindrop. This is an animation looking at a sequence of rays starting at the center. We see it bending as it enters the drop, reflecting off the back surface, and then bending again as it exits. The interesting piece, the critical piece, is that as we look at rays farther and farther from the center, the output angle first gets bigger and bigger and then turns around and gets smaller. Isn't that curious? Let's look at that bit a little bit more slowly just to see it clearly. So what does this mean? I find it easier to see if I plot the output angle against the distance from the center. But first let's make sure we understand what that angle means. So here's you with your back to the sun looking at all the raindrops. The angle we're going to plot is between a line connecting the sun and the back of your head and a line from your eye to some raindrop. So each raindrop has an angle, and we'll see the angle as a position in the sky. Okay, here's the plot. We can see the angle increasing to a maximum angle of a little more than 40 degrees. There's one observation that we can already connect with this plot. There's going to be scattered light from the raindrops out to about 40 degrees, and then none. And that accounts for Alexander's dark band. So next, if we think about it, this plot ought to be slightly different for different colors of light. Here, the peak is going to be the interesting part, so we'll only plot the different colors in the area inside that box that we drew on the plot. Here's that plot, and sure enough, the different colors turn around at different maximum angles. So if I'm looking at a region in the sky corresponding to 42 degrees, we'll only see red. No other colors are there. At much smaller angles, all of the colors are there, and we'll see that as white. Where the green turns around, for example, we'll only see green with a little bit of red, and that happens on through the spectrum. So I hope that helped, and thanks for listening.